Okay, we'll start today's lecture. Okay.
Shut up.
I think I will finish today's lesson about 1 hour time. The second hour will reserve for any consultation or any one who need to clarify something. We actually move quite fast. I have another 3 weeks before the term test. I think we should be able to finish the topics 2 before or on week 7. Week 8 is the revision maybe, then after that is your term test. Okay?
Yeah,
so, okay, still remember what we learned yesterday, right? I guess most of you already very good. If I ask you what is the first order transfer function, what's the formula for first order transfer function?
I don't know.
Y divided by x equal to k divided by tau s plus 1, right? What is y?
Input, output.
Input, right? No, y, the top one.
Yeah.
Top one is output.
Yeah.
The
X
bottom
is
one is the input. Equal to k. K is?
The disturbance.
No, k. Where's my function? This one, right? Y divided by x equal to k divided by tau s plus 1. K is?
The steady state gain.
The steady state gain, right? Actually, the gain is more important this, right? The steady state is just, hold on, yeah. The steady state is just a reference, but the k is actually referred to the gain, alright? Tau is actually the time constant, and s is the unknown in the Laplace form, so it doesn't matter, plus 1. Okay, this is our first order transfer function. Yesterday we learned about 4 disturbance, right? The transfer function, we need to care about the input, the x here. It can be, sometimes we use x to represent the input, sometimes we use disturbance to refer to the input, and sometimes we also call it forcing function, right? So there are 4 types. What are the 4 types we have? Impulse. Ramp. Unit. Unit normally we call step, right? Because unit is just 1. Any step disturbance can be 1 multiplied by, let's say, 5 or multiplied by 10 or any value. So because step disturbance, unit step is 1, okay? And then the last one is sinusoidal disturbance, right? So I guess all of you should now know about this disturbance, right? Each of these disturbance that has a Laplace format. Like for example, this one is for what? This disturbance in this format is for wrong lah.
Yeah, it's RAM.
1 over s is what?
Oh, unit.
Unit, right? The step. This one is for step. The ramp is the next one okay. Ramp is the next one. Ramp is this one, right? The Laplace for the ramp is this one. This one, the previous one is 1 over s. 100 is just the value of the step disturbance, okay? And then after ramp we have impulse. Impulse, the symbol is delta t, which means that the time happen very short. So you look at the chart, right? The time is very short, delta t. So the Laplace format is, this is before Laplace, which means that the impulse delta t multiplied by a amplitude. So after that we have, once we do the Laplace format, the impulse is this one, okay? Of course, for the sine one, you have this format. This one is just mostly for your info. I don't think it will be tested, okay? Then each of this one have different response, right? Remember this one is the first order transfer function when we have a step disturbance. And if you look at this one, the curve is look like an exponential, which means that eventually the disturbance will go to a final level, okay? And the bigger the tau means the slaggy the process, right? Remember there is a, like I got 1 tau, 2 tau, 3 tau like that. The bigger the tau, the time constant, the slower the process. Means that the process dynamic is slower, okay? Of course, we also have this RAM. RAM we actually refer to this chart, this graph itself. This one is actually the disturbance when when disturbance equal to the RAM, okay? Of course, impulse look like this one, okay? It's actually a negative exponential, alright? These are the 4 important disturbance that we put into the transfer function. We will see all these 4 different types of behavior, okay? Right, today we're going to start a new topic, which is the second order system, okay? Second order system is actually quite complicated. We will learn a very basic concept for this second order disturbance. After we complete the second order disturbance, right, the first order and the second order disturbance, these are all the mathematical model related to process dynamic. Once we complete the second order disturbance, we will learn about the controller. So the next section is talking about controller. I will talk about that later, but just bear in mind, now we are reaching the end of the process dynamic.
When the disturbance equal to T, that's not the when is the one.
Okay, a second order system can be there are two way to show a second order process dynamic. The first one is what we call 2 first order multiplied together. If you have 2 first order process, right, multiplied together in series, like for example our tank earlier, you will have a final transfer function in this format. R2 divided by tau s, tau 2s plus 1 and tau 1s plus 2. Over this system, you have 2 different time constants. And when you look at the format like this one, this is what we call second order transfer function or second order process. Or whenever there is a second order differentiation equation in the process, what does this mean? This means that if I have a differentiation equation like this, right? Let's say plus anything x equal to 1. This types of differentiation equation in chemical industry or chemical engineering, later when you come to the reaction or some calculation itself, you will see these types of second order differentiation equation. And this is also can use Laplace transform to solve. But we will not learn how to solve this one for this module itself. But just bear in mind, second order system, we have first one look like this format, the second one look like this format, where we call it differentiation equation process model. So in general, the transfer function of a second order has the following form. Okay, so if you try to expand this one, right, this transfer function itself, you will be able to get this. G is actually the normal, what we call that, the transfer function output divided by input. So this side is actually the output divided by the input, right? Is equal to k divided by tau squared s squared plus 2. You can see over here we have a new unknown here. We call it zeta. This one like a snake is actually zeta. Zeta. This one. Okay. Okay, the zeta. Okay, whatever you call it. It's a small snake then. So 2 times zeta equal to time tau times s plus 1. So for a second order process model, right, is normally in this format. And from this format itself, as I said, K is our process gain, right? The steady state gain. Anything related to K is a gain, similar to what we had earlier. Tau is the time constant which indicates the speed of the response. The smaller the tau, the faster the system responds, okay? So the tau or the time constant indicate the speed of the system. So big tau, like 5 tau compared to 2 taus, right? This one responds faster, okay, compared to the other one. If you refer to your earlier notes, you can see the chart. The 5 tau normally have a more flat slope compared to the other one. The zeta that we have here is actually another coefficient. We call it damping coefficient. Alright? Damping coefficient is to measure the degree of damping of the system, or what we call it, the degree of oscillations in a process response to a perturbation. Well, it's a very long definition, but it's basically telling us that based on this damping coefficient, right, we can see after we put in some disturbance, how good the system buffer or damping from the changes. Every time we change it, right, we change the input or the disturbance, the system will fluctuate. So the bigger the damping coefficient means that it actually fluctuates slower. There are 3 cases of damping coefficient that we will need to study. More than 1 or more than between 0 to 1 or less than 1. There are 3 cases. We will look into that later. But just bear in mind, the damping coefficient is only happen in second order process control, and is to measure how is the degree of oscillations of the process response after a perturbation. Perturbation you can sort of like refer to a disturbance. So anything you disturb the system, because of the second order, it will oscillate. And the oscillation, how fast or how big the oscillation itself determines by this new coefficient. We call it the damping coefficient. Alright? And this format is very important. Just like the first order transfer function, K divided by tau s plus 1. Second order, you also need to understand this format. So from here, if I ask you what is the damping coefficient, I give you a second order question. You need to rearrange it in this format and compare each of these coefficients and find the final value. Okay, that is the main purpose or main things that you need to learn from this second order system. Okay, I'll give you some example. Over here, the example we have for the following transfer function. Determines the process gain K, time constant, and the damping coefficient. So what we have here, G and D. Now the G is referred to output, the D is referred to input, which is the disturbance. And this is equal to 10 divided by 0.5 S plus 2 multiplied by 2 divided by S plus 1. You look at it, we have 2 terms, right? It's actually a second order transfer function. And remember, if you need to find the gain tau or the damping coefficient zeta, right, you must arrange this one into, just now I said, our standard format. Standard format is what? K divided by what? Tau square S square, right, plus 2 zeta tau S plus 1, right? Our second order standard format is K divided by tau square S square plus 2 zeta tau S plus 1, okay? So the format that you have over here, you must convert it into this in order for you to find your K, for you to find your zeta, and for you to find the tau. Okay? Can? So, for me to get this format, first of all, what should I do? I have this 10 times 2, right? if I look at the normal transfer function that I have, normally it's s plus 1, right? If I divide this one with 2, because I want to get s plus 1, I have 5 divided 2 become 10 divided 2 become 5. Okay, 0.5 divided 2 becomes 0.25. 2 divided 2 become 1. I purposely arrange it in this format because that is our common Laplace format from the table. On this side, we have s plus 1, which is our standard format already, so we don't need to touch it. So after I divide 2 over here, I have this new function. The next part is, because I need to compare to something in this format itself, right? If I multiply 5 by 2, I got 10. I expand the bottom part, 0.25 multiply s becomes 0.25 s squared. This multiply this becomes 0.25 s plus 1 s, which is 1.25 s. The last one, 1 times 1 become plus 1. So I expand the bottom, I have a new arrangement like this. 10 divided by 0.25 s squared, 1.25 s plus 1. So if I compare to the standard second order transfer function, the top one is k, and then I know this one and this one represent here and here. Okay? So if I look at this one, what is my k value?
10.
10, right? So k equal to 10, so I solve the first process game that I want for the second order. So k is 10. And what about 1.25 compared to here? I have 2 zeta tau equal to 1.25, right? So before I can solve for zeta, I must solve for tau first, right? Where can I get the tau from?
Tau square equals 0.2.
This one, right? The 0.25 and the tau square. So tau square equal to 0.25. So tau equal to 0.0 something, right? 0.5. Okay. So once you have tau equal to 0.5, I put in here 2 times zeta times 0.5 equal to 1.25. So I solve for the zeta, I should get value 1.25 divided by 2 times 0.5, which is 1.25 also. Right? Can see it. Okay. So for this case itself, if you see this is a second order transfer function or second order process, you must always remember to convert it into this format, and then from there compare to the value that you have in order for you to find gain, tau, and also the new coefficient that we introduced today, which is the damping coefficient. This is what we have over here. The answer k is 10, tau is 0.5, and this zeta is 1.25. Alright, any questions so far? I think it's quite straightforward. Second order, we will not try many more complicated. You mostly need to convert your function into that format and find for this 3 value. Alright, as I mentioned earlier, for the second order, right, we have 3 cases. I have case 1, case B, and case C, A, B, C, 3 cases. And the range of the damping coefficient for zeta more than 1. More than 1 means 2, 3, 4, 5. So any zeta that is more than 1, we call it overdamp. No oscillations, but it's a sludgy response, which means that if I arrange my second order into that format and I realize the damping coefficient is very big, my process dynamic is very slow. And when the process dynamic is very slow, remember last time, early time, I mentioned to you all, I have a big tank and I have a small tank, right? So if I have a very big tank or very big pond, normally the damping coefficient is very big. So for cases like that, when I choose my instrument or I design my process, I can buy the cheaper one, or I can buy something that not so high technology or sophisticated. I can save cost. But if I have some things like I find that my damping coefficient is, let's say, in between of let's say for case B, right, the damping coefficient is equal to 1, which is a critical damp, which means that it's very fast. The response is like immediate after you change it, right, it will back to the original output after a very short period of time. So cases like that means the process responds very fast. So I may need to invest more or buy the system with better instrument, and then my set point and all this for the controller has to be very accurate. And then the last case, which is the C, the damping coefficient is between 0 and 1. Between 0 and 1 means what? Like 0.1, 0.2, 0.3, all the way up to 0.9, and or maybe 0.55, or things like that. Cases like this, we call it underdamped, which is the characteristic is it will have an oscillating response with overshoot. And what does it mean? This is how we look the disturbance or the response itself. But this is only happen to step disturbance. Step disturbance means the changes is only d over s. Okay, d over s for the second order transfer function. If the damping coefficient is less than 1 but more than 0, we will have these types of oscillating response. Which means that if I change the system, at first the system will shoot very high. Then after that it is stabilized. The smaller the value I have, the less overshoot will take place. So among all this, we must choose certain value. If I have a process design and from my second order mathematical models, right, I managed to find my damping coefficient, and if it's too small, then I will need to change my system again to make the damping coefficient in certain range. What are the range that we have or we need? We look at this one. I will read this one and I'll go back to the previous slide. So if you look at this, response of the oscillating and overshoots are obtained only for the value of less than 1. Remember, for more than 1, right, more than 1 or 2, my system did not oscillate. It's immediate go back to the system that I want. Okay, so the damping coefficient more than 1, no oscillation, it just reached. So I disturb the system, it will slowly reach the final output. Okay, then the second one is very large zeta give a sludgy response, which means that very slow. So I don't want a very large. Very large always refer to the big tank or slow reaction. The fastest response without overshoot is obtained for the critical, which is when the zeta equal to 1, right? The value of zeta in the range of 0.5 to 0.4 to 0.8 are often chosen for a specific desired control system. So this range itself is the most preferred range, right? And in this range, the response reaches a new operating point faster than 1. But the response is much less oscillatory than zeta, let's say, equal to 2. What does it mean for the last sentence here?
It's faster than 1, but it's still not as accurate. Like there's still a up slope.
Yeah. So how do we know it's faster than 1? Let's say if I have this chart, right? It reached 1 faster than the damping coefficient equal to 1. Because if you look at the small one, right, when it's disturbed, right, it's actually fluctuate faster. This is my 1. So the small one actually reach faster. But because of the faster disturbance, it take longer time. It's keep fluctuating, right? But if I take 0.4 to 0.8, although it did not reach faster, but it's actually reached the steady state faster. So this is what remains. In this 0.4 and 0.8 range, the response will reach the new one faster, but the response is actually much less oscillatory than 0.2. Okay, these are just different scenario when we have different damping coefficient. You just need to refer back to the chart, or you design a system that's try to compromise or to suit this. Okay, I need you all to understand this concept, but mostly it will not be tested because when you want to test this, you need to know this one more important, how to get this value. Okay, but the response of it, you need to know these cases. The rest of it, how to compare, how to make it faster, or how to implement it into the process control system for the second order system is the higher level, or when you reach the degree or master times, you will need to do a lot of this calculation. Or when someone really studies the process control, then you need to do this more. A lot of times, all this concept or this application itself is much more complicated than what we have with the current technology. Alright, so you just need to have certain concept as your basic, and you really specify in this in future, then you will understand more on all this control. Because you really need to have the control system to run and to test, then you will understand this more. Alright? Until the slide previously, mostly we have done all the process dynamic system. So remember, you have first order, second order. First order transfer function, how does it look like? Second order transfer function, how does it look like? What are the coefficients or the parameter that you all learn from the equation? You have to know. Then how to derive the process control from mass balance is very important. Those are the things that mostly will be tested, especially the tank level, or sometimes we can change the tank level into concentration. Then you need to use the mass balance to derive the process dynamic. And then from there, we'll link you to the transfer function, and then we'll ask you how to, let's say if I have certain disturbance, how's your transfer function change accordingly. Those are the things that we will test it more for this PCI itself, either the term test or the final exam. Okay. Now we'll move on to what we call it closed loop control. From here onward, we'll learn something more on the controller side. Remember your process control. At first, we learned all about the measure variable, control variable, and also the final control element, things like that, right? And before the control variables go to the final control element, it will pass to the controller, right? In the controller, we have set point. And how to calculate the controller set point and the signal that's sent out, we will learn from 2.3 onward, okay? So a quick definition, the simple closed loop control. Still remember what is closed loop control, right? We have closed and open. We have feedback and feed forward. Alright. The closed loop control is a single loop control known as a feedback control. Normally closed loop is a feedback. I measure something and then I send it to the controller. The controller will change the final control elements and it affect the things that I measure. The one we call it feedback control. If I measure something and then I send it to the final controller, it changes the other parameters or other variable. It does not affect the original one. We call it open or the feed forward. Alright. Over here we learn feedback. Feedback control is the closed loop control in which the control action depends upon the feedback or the error signal from the process. That is the difference between the actual process value of the control variables and its desired value. In other words, the corrective actions of the controller depends on the feedback control. A very long definition. But just bear in mind that feedback control, we have something sent out and then we compare with the set point and generate an error. Error will send it to the final controller for the changes. Alright? Whatever corrective action is actually sent out from the controller as a feedback to the system. Okay. Two kinds of controller problem. Okay, who said okay just now? For us? Nicholas. Okay, so I ask you a question now. Okay? Okay. Okay, I don't have the question on the spot also. Alright, two main kind of controller. Now we are referring to the controller problems, right? First one is the servo problem. The other one is regulator problem. These are all definition. A servo problem is deal with the response of the controller to a change in the set point, assuming that there is no load disturbance. What is no load disturbance? The key word here is no load disturbance. Load disturbance refers to the disturbance, right? So for the servo problem, I don't disturb the system by putting the load. The disturbance of the load, right, is actually our inlet, which means that I don't change. The controller change, right, is not because of the inlet disturbance change, but it's more because of my prescribed schedule. Let's say I set the tank temperature. I want to like every day increase by 1 degree. That kind of change, right, is the controller I can set. I set as per the schedule that I want. It's not because of the inlet water temperature change. So the controller that's only changed because of no load disturbance, and it's because of a prescribed schedule. We call it servo problem. Regulator problem is actually a controller that's changed because of the forcing function. Forcing function means disturbance. So which means that the inlet temperature will change, or the inlet's pressure or inlet flow will change. Those kinds of forcing function disturb my system, and then the controller has to respond to the error generated. It's like I need to regulate the system itself. That process or that controller problem we refer to regulator problem. Okay, just in short, or just to simplify the whole things, you said anything that's the controller I can schedule set certain times to respond. That's called server problem. If the controller needs to be like regulate whatever inlet changes, we call it the regulator problem. Alright? This is the one that we learn in topics 1, right? How to reach this one is start from the process. Disturbance come in, we have an output variable, right? And output normally we measure by measuring device. These are the instruments that we normally use, like temperature, pH, or pressure, or flow rate. So we measure something, and then we have a measure output. What is PV here?